All right. The time has now come for the converses of the results that we proved in the previous section. In the previous section, we proved a number of so-called parallel tests, which all say that if a certain condition is met, then we may conclude that lines are parallel. For instance, if we have two lines cut by a transversal so that alternate interior angles are equal, then we may say that lines are parallel. Now we have the converses of those. Which means, of course, that we will be given that lines are parallel, and we will conclude something about a special pair of angles, like, for instance, that alternate interior angles are equal. Now, what's curious about this is that we are in need of a new postulate, and this actually will be our last postulate of the semester, the last postulate until we get to similarity. It is of great significance. For instance, without this postulate, we would not be able to prove the triangle angle sum theorem, one of the centerpiece theorems of the chapter. And also, there is a certain history to this postulate that I'll say just a very little bit about, and then I'll suggest that you go and read about it if you're interested. And that postulate we'll call the Playfair postulate. That's a common name for it, after an otherwise obscure mathematician, English mathematician, I think. It's often also called the parallel postulate, and I'll interchangeably call it both, the Playfair postulate and the parallel postulate. And this is our one postulate chapter. And once this postulate is in place, it will allow us to prove the other results about parallels that we need, and then draw out consequences like, for instance, the triangle angle sum theorem. All right, so I've mentioned what the consequences are. They're all theorems of the form. Of this form, if you have a pair of parallel lines, then some consequence follows, that is, say, that alternate interior angles will be equal, precisely the converses of the results that we had before. And then the question is, of course, how does one prove this? Okay, well, let's reflect, to answer that question, let's reflect first of all on the construction that I introduced in the last lesson, the new construction. The construction was this: if we're given a line and a point not on that line, then we may, through that point, construct a line parallel to the given line. So, for instance, if our given line is M, and P is a point not on it, then we may construct a second line N through P such that M and N are parallel. Now, I have a question, and it's probably the very best question that I'll ask all year long, and I'm almost certain I know how you'll answer this question, because historically in my classroom, students have always answered it in the same way. And my question is this: could we have constructed another line through P, a line Z, say, that was also parallel to M? And a picture will make clear what I need to ask. Could there be, okay, so what we've done is this. So we had a line M, we had a point P not on M. We constructed through P a line N that was parallel to M. So let me make clear what the construction actually has been. So I've constructed a line N through P, parallel to M. And then my question is this: may we also construct through the point P a second line, call it C, that is also parallel to M, so that we would have two lines through P, both parallel to M. Now, invariably, and I always do this every year, I ask students whether this could happen, whether you could have two lines through the same point, both parallel to the same given line. And their answer is invariably no. And they'll often talk about slant or slope or something like that, that if N is at exactly the right sort of slant so that it doesn't intersect M, then if you were to tilt even a tiny little amount, of course you would eventually have to intersect M. It might be far away, miles or, light years away, but you would eventually have to intersect M. Okay, now, for us, that will be true. Okay, we will actually, that will be a truth of our geometrical system. But as always, right, given that we construct a geometrical system in this class, we have to ask what is the status of that truth. Okay, we don't simply say that something is true, but we give it a designation. It's either a definition, a postulate, or a theorem. Right? That's always true in a mathematical system, right? That's always just a basic definition, or it's one of the postulates of the system, or it's something that can be derived from those definitions and postulates. That is, it is a theorem. Invariably, right? In any mathematical system, in any mathematics at all, every statement that is accepted as true is one of the three. Okay, so let us ask the statement. this statement that through a point not on a line, we can have at most one line parallel to the given line. That is, that truth that you know not accept, is it a definition, is it a postulate, or is it a theorem? Well, first of all, as to the suggestion that it is a definition, it absolutely cannot be. Okay, if you just consider the definitions of the relevant terms, like line or parallels or point or anything, any geometrical language that's used in the statement of this truth, there's nothing that says how many lines you can have through a point parallel to a given line. It's not there. Okay, so it has to be a postulate or a theorem. Okay, now, as for the suggestion that it's a theorem, well, historically, most mathematicians wanted it to be a theorem. Okay, now Euclid, and this is no doubt a testament to the great wisdom of Euclid, or the group of ancient Greek mathematicians whose work is collected in Euclid's Elements. He made it a postulate. Okay. And that's ultimately what we'll say as well. Now the form of the postulate in Euclid is a bit different than what we'll give, but it's equivalent. The history here is that though Euclid made it a postulate, mathematicians for literally millennia afterwards were not happy with this. Okay, they did not wish it to be a postulate. Now, of course, it's a very good question why they just didn't accept it as a postulate, because it does seem, I suppose, obviously true. Well, they thought that it wasn't perhaps as obviously true as the other postulates, because it was about, what it said is that, if you were to construct that second line through P, you would eventually have to intersect M, but it might do so very, very, very far away. So perhaps it's not quite as obvious as the other postulates. But whatever the account is of why it is that generation after generation of mathematicians didn't want to count this as a postulate, they didn't want to. They wanted it to have the status of a theorem, which meant that they tried to prove it. Okay, that is on the basis of the other sort of pieces of Euclidean geometry. If one takes out the parallel postulate, they wanted to prove the parallel postulate, and they tried and tried and tried, and they failed and failed and failed. They often thought that they succeeded, but the judgment of history is that their attempts were always failures. Okay? And if you're curious about the history of this, the story about why it is that they wanted this, to have the status of a theorem, there are various attempts to prove it, how those attempts were always unsuccessful. A good place to read about this is the Wikipedia article on the parallel postulate. Hopefully you don't have any prejudices against Wikipedia. It's an excellent source of mathematical information. So I suggest that you go and read that, and perhaps allow yourself to fall into the black hole of Wikipedia, click on links, and just continue to read. So for us, it will not be a theorem. We will call it a postulate, and you can go and read about this if you like. And that is then the Playfair postulate, okay? Or another common name is the parallel postulate, which says that through a point not on a given line, there's at most one line parallel to the given line. Oh, and something else I wanted to mention is this. There have been developments recently in mathematics, sort of meta-mathematical results about the power of certain mathematical systems, what can possibly be proven within them and what cannot be proven within them. And what was eventually proven about Euclidean geometry is that if you take the system and you pluck out of it the parallel postulate, okay, and then ask yourself with what remains, which is often called neutral geometry, if one asks whether one could prove the parallel postulate with that neutral geometry that says nothing about how many lines through a point you could have parallel to a given line, you can't do it, okay? You cannot, with neutral geometry, prove the parallel postulate. It was proven that it can't be proven. And again, if you're curious about this, about how that could possibly have been done, how could you prove results about mathematical systems, what their power is, what you can prove within them, what you cannot, I would suggest that you go and read that Wikipedia article on the parallel postulate, and just click through links and just find out about it. It's really beyond the scope of this course. All right, but I mean, the upshot is this, is that we do have a new postulate, okay? The Playfair postulate, the parallel postulate, which says that if we've got a line and we've got a point not on it, then we may, through that point, construct at most one line parallel to the given line, okay? So if you put that together, with the result from the previous section, what we now have is this, is if we have a line and a point not on it, then we may through that point construct one and only one line parallel to the given line. Okay, so the parallel postulate gives us the guarantee of uniqueness. Now, with that parallel postulate in place, we can begin to prove the consequences, the results of this chapter, of this section. And here's the alternate interior angles consequence, which says that if a pair of parallel lines are cut by a transversal, then alternate interior angles are equal. Okay, so here's the setup. I've got a pair of lines which we say are parallel, that's part of the given, and the third line, the transversal T, that create alternate interior angles 1 and 2. And I've also noted a point of intersection P here, as you see. And what we wish to prove is that angle 1 is equal to angle 2. That is, if lines are parallel, alternate interior angles are equal. As for how we prove this, well, perhaps it'll come as no surprise that we do this indirectly. So let us assume that the measure of angle 1 is not equal to the measure of angle 2. And then, of course, attempt to derive a contradiction from this. Now, if the measure of 1 is not equal to the measure of 2, what this means by the protractor postulate is that we may construct through P an angle that is equal to 1. Okay, that's the 3 shown in the diagram. The protractor postulate says basically that we can construct angles of whatever measure we choose. So if 2 is not equal to 1, then when we construct an angle 3, we may construct a line through P that makes the angle 3 that is equal to 1. Okay, and then ask yourself what follows. Well, angles 1 and 3 are alternate interior, and they are now equal, which would mean that the line that was created to form this angle 3, that is line C, would be, by the alternate interior angles test proven in the previous section, it would follow that angle Z is parallel to line M. But then we would have 2 lines through point P, both parallel to M. And that is contrary to the Playfair postulate. Okay, so that's our contradiction. We contradicted the Playfair postulate at this point. So it then follows, of course, that it's false, that the measure of 1 is not equal to the measure of 2, which means the measure of 1 is equal to the measure of 2, and that's the result. And we can use the alternate interior angles consequence to prove the other consequences. Okay, so you do the first proof by means of contradiction, and then the other consequences can be proven relatively simply, actually very simply, on the basis of the alternate interior angles consequence. And here's one example, the consecutive interior angles consequence. Okay, so we have a pair of lines M and N, which we are given as parallel, like before. And in this case, our angles 1 and 2 are consecutive interior, and we wish to prove that they're supplementary. And let me just show you how straightforward this is. So again, as we did in the previous lesson, let us name an angle that forms a linear pair with one of our given angles. That is angle 3, which forms a linear pair with 1. And notice then the relationships that we have. We know that 2 is supplementary to 1, but we also know by the linear pairs theorem that 3 is supplementary to 1. So we then have 2 angles, namely 2 and 3, both supplementary to the same third angle, namely 1. And so by the same supplements theorem, it follows that angle 2 is equal to angle 3. But angles 2 and 3 are alternate interior. So we now have equal alternate interior angles, which then implies by the alternate interior angles consequence that our lines are parallel. So very, very, very straightforward. And the other consequences that you will prove on the problem set are no more difficult than this.